Scientists, the Large Hadron Collider found something for the first time ever. The thrill of making a discovery is one factor that draws many scientists to their field. You can only imagine the joy felt by the scientific community when a brand new discovery was made lately by the Large Hadron Collider. Some scientists have compared the object to a ghost since it is elusive. What recent discovery has the collider made? Why was it kept a secret for so long? Welcome back everyone. In today's video, we will explain how scientists just announced that the Large Hadron Collider had made a historic discovery about the universe's wonders in this film. Unaware of the Large Hadron Collider, many individuals continue their daily lives. However, the enormous apparatus's discoveries impact every person's life in the cosmos. Consider the most recent particle that researchers have just discovered for the first time with the aid of the infrastructure. The LHC, built over a nearly 17-mile-long underground circular tunnel at the cost of billions of dollars, is the largest and most potent particle accelerator ever constructed. It can be found at the CERN particle physics facility in Switzerland. A particle accelerator is required, but what exactly is it, and why? It is an apparatus that, in controlled setting, dramatically increases the energy of a subatomic particle. Scientists may now examine the subsequent interaction thanks to this. In other words, the LHC enables researchers to test theoretical hypotheses and determine whether they have flaws. The circumstances within a billionth of a second of the Big Bang can be recreated using the LHC. These include events created a few microseconds after the Big Bang and have never occurred naturally. The LHC will almost certainly be mentioned in any subatomic particle headline because it is crucial to contemporary scientific research. Therefore, it was clear what apparatus was utilized when news reports from throughout the globe claimed that physicists had discovered ghost particles for the first time inside an atom smasher. Because neutrinos are infamously elusive, the discovery of the particle in question, the neutrino, opened up an entirely new window for researchers studying subatomic particles. They made progress in understanding the functions neutrinos serve in the cosmos. Neutrinos are abundant in the universe while being difficult to detect or capture. For instance, each square centimeter of your body experiences around 100 billion neutrinos while you watch this video. Of course, you won't feel them come in or go out. These little specks are all around us: cosmic rays, radioactive decay, supernova explosions, nuclear fires produced by stars, and other sources are where they come from. Because they have no electrical charges and almost no mass, neutrinos have escaped detection. Compared to an electron, they are 6 million times lighter. They move so quickly that they virtually don't interact with any matter. They are so elusive that people often compare them to ghosts. You can naturally capture neutrinos if you work extremely hard at it. Neutrinos were found in a few earlier investigations. A sonic boom is produced when a plane flies faster than the speed of sound. Similarly, a particle moving through the water, which slows down light, leaves a faint blue glow in its wake. Researchers adore its shine. However, this method can only identify the signals of neutrinos as they travel through the Earth after arriving from the Sun, not when a neutrino directly hits an atomic nucleus. For example, it provides no information about the kind of high-energy neutron produced when particles collide, as is seen in particle accelerators like the LHC. The LHC cannot find neutrinos by itself. This is partly because the collider uses magnets to guide particles along a circular collision path dotted with detectors. These magnetic traffic signs do not affect neutrinos or other chargeless particles. They thus veer from the detector's course. Scientists from the Phaser collaboration developed the Phaser Nu, a novel neutrino detecting technique to look into this. Lead and tungsten thick metal plates are used to create this Phaser Nu. These plates sandwich an emulsion, which is a collection of layers that can detect light. Making the neutrinos collide with the atomic nuclei of the metal plates is the first stage, which results in the production of particle byproducts. Older photographers will be familiar with the following process. As the particles move through the emulsion arrangement, the emulsion byproducts and neutrino byproducts interact, leaving an imprint of the particle's outline. The researchers discovered that some of the marks were created by neutrinos after creating the emulsion and examining the particle trails left behind. They could identify which of the 3 neutrino particle flavors they had found. The flavors are electron, muon, and tau. This finding gave them confidence that they had chosen the proper location inside the enormous LHC ring to look for neutrinos and that their new detector could indeed see them. In many aspects, Phaser Nu is superior to earlier experiments. For instance, 500 tons of water are needed to produce the Super Cameo Suite. Phaser, in contrast, weighed just 29 kilograms. Additionally, CERN's leftover pieces were used to make it. Recall that we said that there are 3 types of neutrino towns. The most difficult to detect and rarest particles are neutrinos. Tau neutrinos had only been spotted 10 times prior to the development of phaser nu, with the first observation roughly 20 years ago. Although it can discriminate between neutrinos and antineutrinos, phaser nu is strong enough to detect various flares of neutrinos. This is when things start to get interesting. You may remember that antineutrinos modify neutrinos with the opposite charge. Since we previously said that neutrinos lack charge, this knowledge might seem incongruous. Antineutrinos have a lower electromagnetic control than neutrinos, nevertheless. In reality, the negative amount represents a neutron's sleep on the number or a specific type of quantum number, which is used to define the characteristics of subatomic particles. There are many questions about neutrinos for which scientists now lack adequate answers. For instance, many are unsure of the distinction between a neutrino and an antineutrino. Fraser, however, aids in learning more about neutrinos. The Fraser Nu team promised to spend 2022 researching for and catching at least 100 neutrinos. Some of these questions' solutions will aid in addressing issues like how matter is formed and why so much of it is dark. Now, you would anticipate scientists monitoring the sky above when investigating supernovas, wouldn't you? You'll be surprised to learn where astronomers have recently looked. They're searching for hints in trees as part of their mission to learn more about supernovas. They are looking through tree rings for traces of previous supernovas. But how are trees on Earth related to supernovas that occurred billions of kilometers distant from us and billions of years ago? A star frequently passes away dramatically. The outer elements of the star are then dispersed throughout the universe after an explosion. As a result, high-energy gamma radiation is continuously emitted into space for several years. Finding proof of stars dying in trees is what scientists are attempting to do. Despite the fact that there are an infinite number of stars in the universe, supernovae are uncommon. While it is impossible to predict how frequently stars burst, including our own Milky Way galaxy, specific data suggests that humans could experience 1 to 3 supernovae every century. The most recent occurred more than 400 years ago. Professor of Ancient Science at the University of Colorado, Boulder, Robert Bryan Ridge. In tree rings dating back 400 years, he and his colleagues discovered what might be the fingerprint of nearby old supernova. 4 supernovae close enough to Earth to leave their mark in the trait, according to the study, have occurred in the past 150 years. How then does this operate? The key indicator is the presence of radioactive carbon-14, often known as radiocarbon, in large quantities. Compared to the other naturally occurring carbon isotopes, radiocarbon is in tiny amounts on Earth. As cosmic rays from space assault the upper atmosphere, radiocarbon is created there. Cosmic rays interact with the nearby nitrogen atoms when they enter the atmosphere to start a nuclear process that results in radiocarbon. Additionally, the Earth receives a more or less continual supply of radiocarbon because cosmic rays are constantly streaming from space. Additionally, radiocarbon can be found if you know where to look. For instance, you can discover some of this naturally in tree rings, and now and then, a sizable radiocarbon spike appears to be in the tree rings, diminishing over several years after a sizable recognized source of cosmic radiation that elevates solar activity. These surges are typically understood as early solar storms and flare-ups. Trees not close to the equator expand during the mild months, but hibernate during the winter. This pattern of growth and non-growth develops within the tree's internal wood. When the tree is felled, the ring may be seen. The youngest rings are found close to the tree's surface, and as the root gets closer to the center, it gets older. An old tree's age can be determined by counting its rings. Archaeologists used the patterned tree rings in the wood found in ancient constructions to establish when they were built for practical use. Using this knowledge, Breckenridge could predict what may happen to tree rings in the event of a supernova. He reasoned that a close supernova would emit a significant amount of rays. The cells will become more radioactive than one another if they are absorbed by a tree. Ridge and his colleagues reviewed the records to see how well the supernova concept holds up. They created a list of known supernovae from the previous 40,000 years. They could identify the supernova through the nebulous supernova remnants they left behind. Then they contrasted this list with the data from the same periodic radiocarbon spikes and tree rings. How did they find out? All 8 supernovae closest to Earth appeared to have coincided with radiocarbon peak times. For instance, a 3% increase in radiocarbon was seen following the Wheeler supernova, which occurred around 12,300 years ago at a distance of around 800 light-years from Earth. A 2% increase was correlated with the supernova G114 plus Not 3, which erupted around 7,700 years ago at a distance of about 2,300 light-years. Another one is the Weller Jr., which is thought to have taken place around about 2,800 years ago. The Earth saw one radiocarbon spike of 4% during that time. They also discovered supernova HB9, which occurred between 1,004 and 5,400 years ago at a distance of about 4,000 light-years. This one coincided with a 0% increase in radiocarbon concentrations. Currently, researchers are working to confirm the findings of Breaking Ridge. They anticipate that the Three Rings approach will aid in determining the timing of numerous supernovae that have been challenging to date. Additionally, they will learn more about how stars erupt. That is all for this video. Don't forget to like and share this video. See you all soon.